Can you tell us a bit more about the trials that you're completing and how you test?
So in my lab we test molecules more before we get to people. So we test them on things. We test them on cells. So we can grow oligodendrocytes in dishes, in incubators. So we can just grow them on their own, and we can give them different drugs and see whether they divide more or make more myelin sheets or whatever. So we can do that. And then we can also grow them with nerves, because the ultimate job of an oligodendrocyte is to wrap up a nerve in myelin. So it's good to give them nerves to do that on, and we can test how quickly they do that. We also do take slices of brain. So we take brains from mice usually and just chop them up, and then lay the slices down in dishes. And so this is really, it's not live in terms of it's not in an animal, but that these will keep being alive, and they will myelinate for you in culture, and then you can add things and actually see whether the cells move. So it's nearest that you can get to a brain without it being in an animal, and we find that quite useful. And we do use animals as well. Animals don't get multiple sclerosis normally, spontaneously. It's just humans that get that. But what we do is we make little tiny demyelinating lesions in their brains, in the mouse brain, by just doing neurosurgery, and then we can give them drugs to see whether they repair quicker. And that's sort of our range of models that we're trying to use to test. So, for example, I might find a molecule that I think helps oligodendrocytes get into the right place to repair the damage, and I can test it in all of these different models. And if it succeeds with these, then you start thinking, well, maybe this might be something that we could try putting into a patient. So we've got one molecule at the moment that's going through that. So it's been through all the tests in mouse. And we have a pharmaceutical company that's now interested in trying to say, well, would they make this into a drug? So at the moment, what we're trying to do is to test. They have sort of libraries of 1 million different compounds sitting in their pharmaceutical company, or just random compounds that don't know what they do. And so we can say, do any of your compounds act on the receptor as a drug in our system? So that's what we're about to do, is to screen all of their compounds to see whether it works as a drug to change the molecule that we want to change. So that's the first step, and that's as nearest as I've got so far to getting from science to people. So it's been quite interesting, because I've never sort of dealt with pharmaceutical companies in this way, but they've been quite helpful. So we've got a 2-year project to try and find an inhibitor of this interaction we want, that might then be something that might be useful in a human.
And then that's the 5 to 10 years that you were talking about earlier.
Yes. So we've discovered the molecule. We've probably done the 5 years. We've done the first 5 years, and so this is a 2 years to try and see whether we can actually make a drug. And then we'd probably think of another 5 years on top of that before it was in general practice and use. But hopefully, if we get actually a drug that looks okay, then the safety trials and the initial phase 1 trials would be after that, so just in a few years. But most drugs fall, so but that's no mean because they don't work. So people find lots and lots of potential drugs, but very few of them get through to being actually used in human. But that's pharmaceutical companies used to that. But I think the key thing is that you don't set your heart on one molecule. You say, well, okay, that's one molecule, but what we can do is find all these other molecules that might be good for oligodendrocytes as well. And we're taking that one through with a pharmaceutical company. But if that one doesn't work, then we can take another one through, until we find one that does. So that's the way to do it, I think, rather than setting your heart on one molecule. Otherwise you get disappointed. You have to settle your heart on the process. And for me, it's trying to get remyelination to work. And we've got a variety of different possibilities to be able to tweak the cells to make it work better. can get one of those to work, that'd be great.
Yeah. Well, let's hope you do.
Yes, absolutely.
Yeah, definitely keep my fingers crossed.
Yes.
Okay. Thank you, Anna. Thank you.